In this video, I'm going to review quadratic functions, including the different ways that equations of quadratic functions can be written and the different features of the graphs of quadratic functions. Much of this material will probably be review, so I'm going to move through it fairly quickly, but if you feel that you need to go back over any of it, of course you can watch those parts of the video again. Quadratic functions all come from the parent function y is equal to x squared, and they're all related to that function by different transformations. And you'll remember that the graph of y is equal to x squared is just a parabola which opens upwards and has its vertex at the origin. And so the graphs of all quadratic functions are all going to be parabolas. The equations of quadratic functions can all be written in the form y is equal to ax squared plus bx plus c, where a, b, and c are just different constants. And I've stated here that a can't be equal to 0 because if a were 0, this whole x squared term would disappear, and you could see that we'd just be left with a linear function, something with an x, and then c, this constant. So quadratic functions all have equations that can be written in the form y is equal to ax squared plus bx plus c. These are all examples of quadratic functions, and therefore the graphs of all of these would be parabolas. For the first one, y is equal to 2x squared plus 5x minus 1, you can see that a is 2, b is 5, c is negative 1. For the second one, f of x is equal to x squared minus 5, remember that f of x means the output of the function, and so that's the same as writing y here. Here, a is 1, b is 0 because the entire middle term has disappeared, and c is negative 5. For the third one, y is equal to 3 times x minus 1 times x plus 2, it might not be immediately obvious that this is a parabola or that it can be written in this form, but if you FOIL it out, you'll see that you get this kind of equation. And so this is a quadratic function as well. We'll see shortly that this is written in x-intercept form as it is here. The last one, g of x is equal to negative 2 times x minus 3 all squared plus 1, can also be expanded and written in this form. This is called vertex form, as we'll see shortly. So these are all quadratic functions, and their graphs would all be parabolas. Let's review graphing quadratic functions. We're going to start with y is equal to x squared, and then use transformations to graph all of these other ones. We've said that y is equal to x squared is a parabola opening upwards with its vertex at the origin. And the best trick for graphing quadratic functions, for graphing parabolas, is the over 1, up 1, over 1, up 3, over 1, up 5, over 1, up 7 method, where you move over one step from your point and then go up 1 and draw your next point. Then you go over 1 again and up 3, 3 being the next odd number, and draw your next point. Then you go over 1 and up 5 and draw your next point there. Now, you're probably not going to want to draw all these staircases, so you'll just go over 1, up 1, over 1, up 3, over 1, up 5. Then we'd go over 1, up 7, over 1, up 9, continuing up by odd numbers. If you join these with a smooth curve, you'll get a sketch of the right-hand side of a parabola. And because it's symmetric, you can do the same on the other side, over 1, up 1, over 1, up 3, over 1, up 5, and get the other side of the parabola. So that's the graph of y is equal to x squared, and is a good trick for drawing parabolas. Now if I want to draw y is equal to negative x squared, I'm going to do the same but upside down, because you'll recall that that negative is a vertical reflection in the x-axis. Over 1, down 1, over 1, down 3, over 1, down 5. So that's y is equal to negative x squared. If I want to do y is equal to 2x squared, that 2, recall, is a vertical stretch by factor of 2. So instead of going over 1, up 1, I'm going to go over 1, up 2, then over 1, up 6, over 1, up 10. I'm going up by double the amount that I did before. Again, my vertex is at the origin. Over 1, up 2, over 1, up 6, etc. And the same on the other side. So that's a vertical stretch factor 2, and that's the graph of y is equal to 2x squared. If I wanted to draw y is equal to x squared minus 3, remember that's a vertical translation down by 3, and otherwise the graph is unchanged. So I just move my vertex down 3, and then I go over 1, up 1, over 1, up 3, etc. And I'm just going to draw part of this one because I think you get the idea. If I want to draw y is equal to x minus 7 all squared, recall that because I've replaced x with x minus 7 inside the brackets, inside the function, this is a horizontal translation. And also recall that horizontal translations are counterintuitive. So x minus 7 means that I'm actually going to be moving the whole function to the right by 7. So I start with my vertex, therefore, instead of at 0, 0, at 7, 0, and then I just follow the same over 1 up 1, over 1 up 3 pattern that I had before, because there's no vertical stretch. Lastly, if I wanted to do this one, this has a vertical reflection, vertical stretch, and has both horizontal and vertical translations. The easiest way to graph functions like this are to find the vertex first. Remember, this means we've moved it left by 8 and up by 5. So I go left 8 and up 5. And then the negative means I've reflected it vertically in the x-axis, so it's opening downwards. And the 2 means instead of going over 1 down 1, I'm going to go over 1 down 2 on both sides. And then over 1 down 6. So this is going to be a sketch of the graph of y is equal to negative 2 brackets x plus 8 all squared plus 5. Again, do the translations to find the vertex and then apply the trick over 1 up or down, however many, based on the vertical stretch factor to graph the rest of the parabola. A few terms to know, therefore. Vertex we've seen several times. Also note that if the parabola is opening downwards like this, then the vertex is going to be the maximum y value that the function attains, because it's going up until you reach that maximum and then it turns around and goes back down. If the parabola is opening upwards like this, then the vertex is going to be the minimum y value. Those are important ideas, especially in solving problems, and we'll look at them more in a future lesson. Axis of symmetry is the line that goes through the vertex and divides the function vertically into two symmetrical halves. In this case, because we've moved the function left by 8, the axis of symmetry is x is equal to negative 8. Whereas in this case over here, we've moved the function right by 7, so the axis of symmetry is the line x is equal to 7. In the original function, it was the line x is equal to 0. And also be aware of the terms x-intercept and y-intercept, which you've seen many times before. Now that we've seen that, let's apply that same kind of thinking to finding the vertex and axis of symmetry of parabolas when we're just given the equation. So here's the first one, y is equal to 2 times bracket x plus 3 all squared minus 2. Now what we've seen is that that 2 is a vertical stretch factor. That's not going to affect either the vertex or the axis of symmetry, but what will are the translations, this horizontal translation and this vertical translation. So remembering that horizontal translations are counterintuitive, the parabola has actually been moved from its original starting point 3 left, and it's been moved 2 down. That means that its vertex, which used to be at 0, 0, is now going to be at negative 3 because we've moved 3 to the left, and negative 2 because we've moved 2 down. And the axis of symmetry, which, as we saw previously, goes vertically through the function and through the vertex, will have the same x value as the vertex, and is just the line x is equal to negative 3. So that's the axis of symmetry. Here's another similar example. In this case, we've got 3 times x minus 9, all squared minus 5. Because this is x minus 9, we've moved the function from its starting point 9 to the right, and the negative 5 means it's been moved 5 down. The vertical stretch factor of 3, again, won't affect either the vertex or the axis of symmetry. So the vertex in this case is 9, negative 5, because of the move 9 right and 5 down. And the axis of symmetry is going to be x is equal to 9, again, going through this point. This last one is a little bit more involved. Here, this is written in what we call standard form, not in vertex form, as these previous two have been written. So we need to put it in vertex form in order to solve the question. Actually, that's not quite true. There's several ways that we could solve the question. which we will look at in more depth in a future lesson. For now, we're going to put it in vertex form. So the way we're going to do that is completing the square. If you don't remember how to complete the square, then you'll probably want to go back and watch the completing the square video. I'm going to go through this relatively quickly. We factor the common factor of 2 out of the first two terms to get x squared minus 6x and leave the 13 outside. Then we take half of negative 6, which is negative 3. I'm going to write that up here. I square that and put that back inside the brackets for plus 9, and then subtract it back off, which is minus 9. Close the brackets, and then I've got the 13 outside. Now I've got a perfect square trinomial here, which is the point of this, but I need to kick the negative 9 out first by multiplying it by 2. That's the 2 there. So I get 2 times x squared minus 6x plus 9 left inside the brackets, and then I have minus 18 from minus 9 times 2 plus 13. Next, I'm going to factor this, which is a perfect square trinomial that factors to x minus 3 all squared. Combine those, and I get minus 5. Again, if that was fast, because you're having trouble with completing the square, you're going to want to go back to that video. Now we've got it in vertex form as we had here, and we can see that we've moved the function 3 to the right and 5 down. Therefore, the vertex is going to be 3, negative 5, and the axis of symmetry is x is equal to 3. So that's finding the vertex and the axis of symmetry. Next, let's look at finding the x-intercepts. Recall that to find the x-intercept of any function, you have to set the y value equal to 0. So for quadratics, if we're given something in this form, y is equal to x minus 2 times x plus 5, we set y equal to 0. Then we use what I call the zero product rule. That is, if the left side and the right side are equal, and the left side is equal to 0, then the right side has to be equal to 0. If the right side is a bunch of things multiplied together, then one of these, either x minus 2 or x plus 5, must be equal to 0, and we set each of them equal to 0. So x minus 2 is equal to 0 would make this 0, therefore the whole right side would be 0, and the statement would be true. Or x plus 5, if that's equal to 0, then the right side is equal to 0, and the whole thing is true. Now we just solve each of these little mini equations, and we get x is equal to 2, or x is equal to negative 5. And so the two x-intercepts of this parabola are at 2, 0, and negative 5, 0. For something simple like this, you might be able to jump right to 2 and negative 5 without doing this intermediate step. Sometimes, though, it can be a little bit more confusing. In this case, we get f of x is equal to 3 times 2x minus 5 times x plus 1. Remember, f of x is the same as y, so we set that equal to 0. Now, the 3 can't ever be equal to 0, so we can ignore that, but 2x minus 5 can be, so we set 2x minus 5 equals to 0, and x plus 1 can be, depending on what x is, so we set that equal to 0 as well. Solving this one is very straightforward. X is equal to negative 1, and this one just requires one more step. 2x is equal to 5, therefore x is equal to 5 over 2. And so the two x-intercepts are at 5 halves 0 and negative 1, 0. Sometimes people skip this intermediate step with this one and then make a bit of a careless error. So for the first few times at least, you may want to go through these steps. This last one is one step more complicated because we're given the function in standard form, and now we need to convert it into this factored form or x-intercept form. And that's straightforward to do. All we have to do is factor it. And in this case, it's a simple factorization. We get x minus 2 times x minus 3 because we're looking for two things that multiply to 6 and add to negative 5. Setting each of those equal to 0, if I skip this intermediate step, I get x is equal to 2 or x is equal to 3 as my two possible answers. So this function will have x-intercepts at 2, 0 and 3, 0. So we can see then that quadratic functions can be written in three different forms: standard form, vertex form, and factored or x-intercept form. And each of them is convenient for different purposes. Standard form like this, for example, y is equal to 2x squared minus 4x minus 6, is often the way that we're asked to present solutions, and it makes the y-intercept clear. In this case, the y-intercept is just the last number, c, in the formula, because if you imagine plugging in zeros for all the x's, which is what you need to do to find the y-intercept, all you'll be left with is this last number here. So the y-intercept of this parabola would be the point 0, negative 6. We also looked at vertex form, which has this kind of form. As an example, if I took this parabola and completed the square I could change the form of the function to vertex form, and I would get y is equal to 2 times x minus 1 all squared minus 8. Same function, just written in a different form. And the nice thing about vertex form is, as the name suggests, it makes the vertex clear. This parabola has been moved from its vertex being at the origin. We've moved it 1 right and 8 down, so its vertex is going to be the point 1, comma, negative 8. And we can also see that the vertical stretch here of 2 is the same as it looks like it was up in the standard form as well. These are the same quadratic function, just different forms. Again, to get from standard form to vertex form, you complete the square. To go the other way, you would just expand. Don't forget that this squared here means you are multiplying x minus 1 times x minus 1, so you need to FOIL the whole thing out before multiplying by the 2 and then subtracting the 8. Also, we can convert from standard form to factored form by factoring. And the nice thing about factored form, or x-intercept form, is it tells us what the x-intercepts are going to be. If I took this and factored it, I would get y is equal to 2 times x plus 1 times x minus 3. And this tells us that our x-intercepts are going to be the points -1, 0, and the point 3, 0. Because subbing in 0 for y and solving the quadratic equation would give us x's of -1 and positive 3. Again, to get from standard form to factored form, or x-intercept form, you factor. To go the other way, you expand. And there's not a direct way of going between factored form and vertex form. You have to go through standard form first. So let's take that same quadratic function that we just looked at, y is equal to 2x squared minus 4x minus 6, and derive some information from it and then sketch it. The first thing that we're asked to do here is find the x-intercepts. So to find the x-intercepts, we want to change from standard form, which we've got here, to factored form, or x-intercept form. Remember that the first type of factoring you should always look for is common factoring. And if you do that here, you can common factor out a 2, which leaves you with x squared minus 2x minus 3. And then it becomes a lot simpler to factor. It's not one of those trinomials with a non-1 number at the front. So now we can just factor that to x minus 3 times x plus 1. And then we know that the x-intercepts are going to be the points 3, 0 and -1, 0. And that's just what we saw back in this example. So we can draw those in the graph. 3, 0 is going to be here. -1, 0 is going to be here. The axis of symmetry is going to be the vertical line going right down the middle of the function. We know that this is going to be opening upwards because the leading coefficient is positive, but that doesn't actually matter for the axis of symmetry. We know that it's got to run between those two x-intercepts, so it's got to run like this. It's going to be halfway between x is equal to 3 and x is equal to -1, so it's going to be the line x is equal to +1. And you could find that algebraically if the numbers were trickier by taking 3 and -1, adding them together and dividing by 2. So the axis of symmetry is the line x is equal to 1. That also means that the vertex is going to lie somewhere along this axis of symmetry, and because it's opening upwards, we know it's going to be down here somewhere. Remember that the equation of any function gives us a rule for finding the y value from the x value. So in order to find the y value of the vertex, knowing that the x value of the vertex is 1, we just take 1 and sub it into the equation. So y is going to be equal to 2 times 1 squared minus 4 times 1 minus 6 is going to be 2 minus 4 minus 6 is equal to -8. That means the vertex is the point 1, -8, and that's down here, just off the bottom of our screen. So the parabola's got to be opening upwards, and remember we said that there's a vertical stretch factor 2. That means that I'm going over 1 and up 2, over 1, up 2 on both sides, and then I'm going to go over 1 and up 6, and we've drawn it correctly because that is going to hit our x-intercepts. The next one would be over 1 and up 10, but that's going to get us off the graph. So we'll just draw that for now. So that's my sketch of y is equal to 2x squared minus 4x minus 6. One more thing to review about quadratics here, and that's how to tell if something is a quadratic when you're given a table of values. And the key is to remember that quadratics have second differences that are constant. It's easiest to see what that means from an example. So here's our parent function y is equal to x squared. We're given x values from -4 to 4, going up by 1. If I fill in the y values, therefore, I'm just squaring the x values. So I'll get 16, 9, 4, 1, 0, then back up 1, 4, 9, 16. Now, to get the first differences, I'm going to subtract one y value from the one next to it. I'm going to work up from the bottom here, but really you could do it either way. So 16 minus 9 is 7, 9 minus 4 is 5, then I get 3, 1, 0 minus 1 is -1, -3, 4 minus 9 is -5, 9 minus 16 is -7. So those are different, but if I start here and look at these, what we call the first differences, because they're the differences between the y values, and do the same thing, I'll get the second differences. So 7 minus 5 is 2, 5 minus 3 is 2, 3 minus 1 is 2, and as you can see, these are all going to end up, if we're careful about our negatives, being 2. The second differences are constant, and that tells me that this is a quadratic if I didn't already know it before. Here's an example question then. Does this table of values describe points on a quadratic function? Two things to note. You need to make sure that the points are in increasing order of x value. So if this -8, -66 point, for example, were written down here, you'd need to reorganize the table of values before you could use this approach. You also need to make sure that the x values are going up by the same amount each time. Here they're going up by 2 each time. In the previous example, they were going up by 1 each time. But you need to be sure that they're going up by some consistent number each time to be able to use this approach. Once you've reorganized the table, if you need to, here it's already in order, then you can use the approach that we just looked at. So we subtract successive y values. -34 minus -10 is going to give me -24. -10 minus 6 is -16. 6 minus 14 is -8. 14 minus 14 is 0. 14 minus 6 is +8. Then I get +16, +24, and +32. Repeating the process then, and again being careful of my negative signs, I'm going to find that I get -8 all the way through. That means the second differences are constant. That means that this is a quadratic function. So yes, this is a quadratic function because the second differences are constant. So that's a review of some of the key features of the graphs, tables of values, and equations of quadratic functions.